Today's lecture is all about boundary conditions and different types of boundary conditions that we encounter in science and engineering. It turns out that in most problems, the boundary conditions are the most difficult part of the problem. The governing equations are usually not that bad. It's usually the heat equation, the wave equation, the bending equation. The governing equation's set. There's only so much you can do to the governing equation. It's really what's happening at the boundaries that dictate the overall phenomena of the problem. And you already saw that in the last lecture that very seemingly benign change to the boundary condition made a dramatic difference in the way we solved it in the overall profile of the temperature. Now we're going to cover more of that today. What are the different types of boundary conditions that we might encounter in science and engineering, and how do you pose that mathematically? Now, just to get warmed up to the broader question of boundary conditions, let's consider a small little variant of the problem that we've been working on. We're just going to slowly build on the problem that we've been working on. So we have a slab. It's a one-dimensional problem as a function of x going from 0 to L. We'd like to solve the temperature profile inside the slab when the left-hand boundary is fixed in a hot reservoir at some temperature T1. Initially, the slab is at some 0 temperature all the way across at time t equals 0. And on the right-hand boundary, in the previous lecture, it was set to ice bath, 0 temperature on the right-hand side. But in this case, we're going to consider a different boundary condition altogether. Not a fixed temperature, but a fixed derivative. In particular, we're going to consider, in this case, what's called an insulated boundary condition. An insulated boundary condition is one where there's no heat flux leaving this boundary. In other words, the overall flux Q is equal to 0 at this boundary, in this case at x equal to L. So what this means from the perspective of the temperature profile is the following. The spatial derivative of the temperature at x equal to L must be equal to 0. And this is again coming from the fact that there's no heat flux leaving the boundary at that surface. And this is called an insulated boundary condition. Just like that. So our goal, as usual, is to solve for the temperature profile inside this material as a function of position x and time subjected to these two different boundary conditions, one on the left set to a particular temperature, one on the right set to no heat flux leaving that surface, and with the initial condition at all positions x, it's equal to 0 temperature. So just like the last lecture, we already know that the left-hand boundary, the non-homogeneous temperature, is going to cause a problem. So just like last time, let's split the problem into two parts. So here's our governing equation, the heat equation, which has not changed at all. The only thing that's changed are the boundary conditions. And we already know that we need to separate into a transient part and a steady state part because of this non-homogeneous boundary condition. Now, because the governing equation has not changed at all, the solution procedure to get to a general form of the transient and steady state profile are the same. Let's just write down the solution for the transient and steady state, including the constants of integration. Here are the transient solution and the steady state solution. Once again, the reason why we're able to just write down these solutions is because the governing equation written right here has not changed at all. And if you go back to your notes from the very first time we solved the heat equation to the last lecture we solved it for the non-homogeneous boundary condition, up to this stage where you separate the variables, you get an OD for x, OD for time, the whole procedure is the same all the way through here. So nothing has changed. Of course, with the last lecture, we had the steady state solution that we had to solve separately. So this part is new, but the transient part is the same all along. Now, this is where we need to be more careful. From this point onward, the boundary conditions will start to matter because we now have to figure out what the constants of integration B, C, E, and F are. All right, let's apply the boundary condition on the left-hand side following last lecture's procedure. So let's apply the boundary condition on the left-hand side at x equal to 0. We have two conditions that we need to satisfy, just like the last lecture. First, to homogenize the boundary condition, the steady-state solution needs to take the non-homogeneous temperature T1. The transient part needs to take the temperature of 0. Now, the steady-state part at x equal to 0, E times x goes away. We just get F. So F is equal to T1, just as before. Now the transient part, at x equal to 0, cosine becomes 1, sine becomes 0. Therefore, c sine lambda x dies. We get b times an exponential is equal to the right-hand side 0. Let's write all that down. All right, so the boundary condition on the left-hand side, as before, tells us that one of the constants is equal to f, t1, other one, b, equal to 0. Now, so far so good. Let's go to the right-hand boundary condition and apply the condition where the derivative of the temperature with respect to position x is equal to 0 when evaluated at x equal to L. Let's do that. So we have, at x equal to L, the spatial derivative of the full temperature profile must be equal to 0 when evaluated at x equal to L. All we're going to do is plug in our entire temperature profile that we have so far. Again, now our F, which is T1, and B, which was 0, is gone from this expression. So we only have the constants of integration E and C left over, along with the eigenvalues lambda. We take the derivative just as usual. So the derivative boundary condition on the right-hand side, no big deal. Just take the derivative. No big deal. And remember, the differentiation of the Fourier series just goes straight through. So this, we can just differentiate term by term, and there's no problem at all. All right, so we get this equation right here. Now, we've made this argument over and over again, and we're going to make the same argument again. This equation, or this equality, has to hold for all time t. Now, if this term were to stay, that means that this constant of integration E would be a function of time, which can't happen. Therefore, both of these terms each have to be equal to 0, which means that E must be equal to 0, and this second term must also be equal to 0. Otherwise, this exponential term is going to stay. Let's first write down E is equal to 0. All right, so E must be equal to 0. Now, the second term right here. One way to make that 0 is if C were equal to 0. But if C were equal to 0, then we get a trivial solution back here. Same sort of arguments we've been making. Therefore, instead of making the constant C equal to 0, we need to make cosine of lambda L equal to 0. In all the examples we've been using, it was sine lambda L equal to 0. Here's a first instance where the cosine of the argument must be equal to 0. No big deal. We just keep going as we always have been. So now, when you think about when do cosines equal 0, it's every pi over 2 cycle. So at the top, pi over 2, 3 pi over 2, 5 pi over 2, so on. A compact way to write this is this way. So lambda L is equal to pi over 2 times 2n minus 1. So now n equal to 1, 2n minus 1 is equal to 1, and therefore you get pi over 2. At n equal to 2, 2n minus 1 becomes 3, and therefore you get 3 pi over 2, and so on. So the indices n start at 1 and go on with integer values. 1, 2, 3, 4, all the way to infinity. So, as before, the second boundary condition gave us the eigenvalues lambda. And once again, because there's many possible solutions n where this applies, we use superposition to add up all the solutions to get our most general result for this expression right here for both the steady and the transient. Let's write that down. All right, so now I've written the full solution as we have it as of now, where we have the steady state solution, which is just T1, because E is 0, which means that the linear x term goes away, and we only have f is equal to t1 left over. So this is our steady state solution t1 plus a summation of n going to 1 to infinity. Now, important point. The eigenvalues here from this boundary condition dictates where the summation begins. Here, it begins at n equal to 1, and therefore this summation, the lower bound, must begin at n equal to 1. That's the first possible solution. Therefore, we have n of 1 to infinity of c sub n, which we come from here, times this exponential in sign with the eigenvalues lambda n that came directly from our boundary condition. Now, all we need to get is our constant c sub n, which we get from our initial condition as usual. Right here, we've applied our initial condition, which is telling us that for all position at time t equals 0, the temperature is equal to 0 all the way across the material. Now, plugging in our solution up here on the upper right, over here on the left-hand side, we just get t1 plus the entire summation must be equal to 0. Now, it should be pretty clear at this point, as Fourier series expert users, that we could just now move the t1 onto the other end, so it becomes negative t1 on the right-hand side. And now this is just a Fourier series for the function t1, which is just a constant function. So now we can very easily obtain our coefficient c sub n. So now I've just taken the Fourier series coming from this initial condition for the coefficient c sub n. It's just the usual definition where we're just taking the Fourier series of the function negative t1, which is the left-hand reservoir boundary condition that penetrates all the way through at steady state. We expect the temperature profile to be t1 all the way across. Multiply it against the Fourier series for the sine series with the eigenvalues given by this expression right here. So this is it. This is the solution of the temperature profile inside this material for the condition where it's 0 temperature, left-hand boundary instantaneously increased to T1, the right-hand boundary always 0 flux, 0 heat leaving that boundary. Now, I've coded this temperature profile over in MATLAB as usual, so let's take a look and see what it looks like. All right, so over in the screen here, I've just coded up this analytical pen and paper calculation that we have. We have the heat equation solution here. This is the coefficient integral, so C sub n is equal to 2 times the integral of negative 100. I just set T1 to equal to 100 degrees. It's negative T1, which is negative 100, times the sine series of, here are the eigenvalues, going from 0 to L. I've set L equal to 1. Now, the lambda n is equal to here. I've snuck in there a factor of alpha and squared it, but again, once again, this is just an exponential prefactor. I'm adding up the solution C sub n as the sine series plus this exponential. And I'm going to evaluate this for 30 Fourier series terms in the summation. And I want to first plot it at specific time points going from 0.01 all the way to 30. Let's evaluate this. You get a profile that looks something like this. So on the y-axis, I'm plotting the temperature, which varies with position and time. The x-axis is just the x position. The black line that runs all across at temperature of 0, that's the initial condition. It's initially 0 temperature all the way across. And at time t equal to 0, immediately the left-hand boundary jumps up to a temperature equal to T1, which is 100 in this particular case. And the blue curve is at 0.01 seconds. As usual, you can see the steep increase that meets the boundary condition and then does a bunch of oscillations due to, again, the Gibbs overshoot. And as we wait longer and longer in time, it goes to the orange curve, yellow, purple, and then to the green. Now, notice that the boundary conditions are always satisfied. On the left-hand side, the temperature is always fixed at 100, T1. On the right-hand side, now, unlike before, the temperature is varying. It's now lifting off above 0 temperature, but look, the flux or the derivative is always equal to 0. So the slope at the boundary is equal to 0, 0, 0, all the way across. If you take the slope at x equal to 1 at that boundary, the slope is going to be equal to 0, as specified in our boundary condition. Now, so there's this kind of interesting thing about boundary conditions that we're already noticing. When you specify the flux or specify the derivative of the temperature, it's kind of like a weaker statement about your knowledge of that boundary condition. It's a weaker boundary condition in a way because you don't know what the absolute temperature is. In this particular case, the temperature is unknown. I don't know that at temperature at time t equal to 30, the temperature is equal to 40. All I know is that the slope is equal to 0. That's all I can tell you. I can't tell you what the temperature is. In contrast, when you say the temperature is equal to 100, it is going to be 100 at all times. Of course, you can't specify the slope in that case, but in a way, it's a stronger boundary condition, a stronger statement you can make about that point. Now, I have an animated version of this, so let's play that as well. It's the exact same equation, just now animated. Okay, this goes way too quickly, so I'm going to play that again, but dynamics are so fast that if you must blink, do it now, because the initial part is so fast, and the initial part contains a lot of the interesting things. Okay. I'll play it once more. Initially, it's 0 all the way, and then slowly, the temperature starts coming in towards the boundary. So the idea is that at the left-hand boundary, this side is where the heat is coming in from the infinite reservoir on the left-hand side. It's being pumped into this domain, which is then heating up this entire material. And at steady state, as you would expect from the solution, goes up to a temperature of 100. That's TSS as a function of x is just equal to T1. That permeates all the way across. Okay, so now that you've seen, I'm going to play it one more time because I'm proud that I wrote this up. Okay, so let's now talk a little bit more broadly about the different types of boundary conditions that you might encounter in science and engineering. Sorry, before going into the different types of boundary conditions, I wanted to mention one thing about the problem we just did and about homogenizing the boundary condition. This is actually important, and a lot of students missed this when I was teaching this, so I wanted to make sure I insert this because they got confused about how to homogenize the boundary conditions appropriately. Let's review, once again, the problem we did earlier. Forget about the insulated boundary condition, just constant temperature, where you know the function value at both boundaries. Now, we have non-homogeneous boundaries at both boundary conditions, and we have to split it into two problems. One problem right here, which is the steady state solution, where you put your non-homogeneous boundary condition both on the left and the right, and you solve your purely steady state heat transfer problem, and you add that plus another problem which has the transient part. So in this particular case, you take your temperature value to be T of 0, both on the left and the right. And in this particular case, the problem on the right was your homogeneous boundary conditions. So far, so good. I think you guys are all really good at doing this procedure. Now, the problem we just did right now, where you had an insulated boundary condition, was a different class of boundary conditions over here on the right-hand end. We kept the constant non-zero temperature on the left, but we set that the flux, or the derivative of the function you want, is equal to 0 on the right-hand boundary. We still have to split it into two parts. Recall the problem we just did. We split it into two parts. One part was the steady state solution, where you took the non-homogeneous boundary condition of temperature equal to 100, or a non-zero number on the left-hand side. And on the right, you actually wrote the derivative of the temperature, partial t partial x is equal to 0. And this right here was our steady state solution. Plus, we added to that a transient problem, where now you notice that it's 0 temperature on the left, but on the right, it was 0 derivative. This was not the 0 temperature boundary condition, but the derivative was equal to 0. And so our homogeneous boundary conditions in this particular case is that problem on the right. And a lot of students make a mistake of saying, oh, I'm going to homogenize my boundary condition. The derivative boundary condition, I'm just going to make it a constant temperature boundary condition of 0. That's not correct. because now what you've done is to move between different types of boundary conditions, one where you know the function value to one where you know the derivative. And so you don't want to mix those up. If you are given a derivative boundary condition on the right, you need to keep the derivative boundary class type over here and set that equal to 0. That is your homogeneous boundary condition. So you have to retain the same boundary condition type. And for that, that's the next part in this lecture where I'm going to explain to you there's 3 different classes or types of boundary conditions. We'll get to that shortly. Suppose we were to redo the problem we just did, where I gave you a temperature on the left-hand side, so the function you want, t, is known. It's non-homogeneous on the left. But the derivative of that is also non-zero. Let's just say you have a water jacket that it's designed to remove a certain amount of heat at a certain rate from your reactor. Then this one's going to have a fixed slope on the right-hand boundary. So now you have non-homogeneous boundary conditions on both ends. Whereas in the previous example, the problem we just did earlier in this video, we had non-homogeneous boundary condition on the left, but this one, the insulated boundary condition, this was already homogeneous as is. Now this one is non-homogeneous on both ends. So you still have to separate into 2 problems. One problem, which is a steady state solution, is going to be t of 100 on the left, and then you take your non-homogeneous boundary condition here, and this becomes your steady state solution. You add this, the transient solution, and notice here that on the right-hand boundary, we're taking the 0 derivative to, the temperature derivative to be 0. So notice that this is not constant temperature equal to 0, but the derivative equal to 0. That is your homogeneous boundary conditions. And again, a lot of students put t equal to 0 as the homogeneous boundary condition, but you don't want to do that because you want to make sure you retain the same boundary condition type. If you're given a derivative boundary condition, keep the derivative boundary condition. But now we've gone from 5, which was non-homogeneous. That was blasted over into the steady state solution here. We have 0. That is a homogeneous boundary condition. So a homogeneous boundary condition is essentially you have a given class type of your boundary condition, which I'll explain next. And that being equal to 0 is your homogeneous boundary condition. All right, with this, we can now move on to the different classes of boundary conditions. And there's 3 different ones. And those, when the right-hand side is equal to 0, is the homogeneous boundary condition. All right, let's go to the different types of boundary conditions next. Let's talk a little bit about the different types of boundary conditions that you might experience in common science and engineering problems. Now, boundary conditions. We need to specify one condition at x equal to 0, one condition at x equal to L. You've seen 2 of these variations already. Let's write the first common one down. The first one that you've already seen before is a situation where you have the function that you want to obtain, like the temperature, and you know what the temperature is at the boundaries, at x equal to 0 and x equal to L. So this is, in fancy math lingo, will be called a Dirichlet boundary condition. Let me write that down. Just like that, Dirichlet boundary conditions. It's a very good way to sound very smart and fancy. Say, oh yeah, I just applied Dirichlet homogeneous boundary conditions on both ends of my slab. Dirichlet. Kind of sounds like, oh yeah, I'll take a Pinot Noir with the steak. Dirichlet boundary conditions on the edge. Dirichlet. That's the first type. The second type is where you don't specify the function value, but you specify the derivative at the values, the ends. Okay, so here's an example that you just saw with the insulated boundary condition, where we specify the derivative at a particular boundary as opposed to the function value at that boundary. And just like you saw in the previous example, you can mix and match. So on the left-hand boundary, previously we had a Dirichlet boundary condition at x equal to 0, temperature was equal to T1, whereas on the right-hand side we had what I'm going to teach you how this is called, that boundary condition on the right-hand side, x equal to L. Now, this is called, I'm going to write it down and ask how you're going to pronounce it. This boundary condition, if you say Newman, that's not good enough. Neumann boundary conditions. oh yeah, I applied the Neumann boundary conditions on the right and the Dirichlet boundary conditions on the left. That's what you should say if you want to sound very impressive to your parents or your friends over dinner. Okay, you've already seen these before. There's a third class of boundary conditions, which is also very common in science and engineering. And it is the mixture of both the function at that point plus the derivative at the same boundary. So what would a mixed boundary condition look like? The final common type of boundary condition that you'll find is, once again, a mixture of both the function value and the derivative, a mixture of the Dirichlet and the Neumann boundary condition. So we have some constant C1 times the temperature value at x equal to x naught. It could be at x equal to 0, or it could be x equal to L at some boundary, x naught, plus C2 of the derivative at that same boundary. That could be equal to some constant or some function of t. It could be a constant or a function of t. Now, this, like I said, has elements of both because you're adding the function value and the derivative together and saying that that together is what specifies whatever is happening at that boundary. And this boundary condition is called Robin boundary condition. I know many of you said Robin. You wouldn't sound fancy that way. It's the Robin boundary condition. So here are the common boundary conditions. Dirichlet, Neumann, Robin boundary condition. Now, Dirichlet and Neumann, you probably have an idea of what that feels like. You kind of know what the temperature is, or what the velocity is, what the concentration is, or what the flux and the yeah, I can kind of see the slope being equal to some value or equal to 0 at some boundary. When would we see a mixed boundary condition, a Robin boundary condition? When would we see that? Let me give you an example. Let me give you an example of a situation where we might see the Robin boundary condition using an example where it's mechanical chemical engineering aspect. Suppose you were at some microelectronics company, and this is some material that is temperature sensitive. So you want to make sure you put this with a coolant that will draw heat away from the material to prevent this material from overheating, because if it overheats, it might cause the material to melt, it might cause the resistance to change. It's a very sensitive electronic part, maybe a GPU that needs to be fan cooled. Maybe that's a better example. Some kind of very specific thing that we're all familiar with, like a GPU or a CPU that's heating up, and your computer or your laptop has fans. It has fans to make sure that your GPU, your CPU, doesn't overheat. So there's going to be some convective cooling of air or some kind of fluid at the end or across the surface of your material to prevent the temperature from getting too high. So let's suppose it's air. There's some fan that's blowing on your laptop or inside of your computer that's blowing a colder air across your surface that's overheating. Now, when you want to solve for the temperature profile inside your material, there's going to be a Fourier's constitutive relation, Fourier's law of conduction, that you would need to apply right at the boundary at x equal to L. So there's going to be a temperature profile inside this material that you're trying to solve for. There's some temperature profile. And at the boundary, you don't quite know what that temperature is because all you're doing is blowing cold air over it. But you do know that the heat leaving the boundary at that point, the slope at that point, needs to be equal to the heat entering this airspace. So conservation of energy applies at the boundary, and therefore heat leaving the material must be the heat that's being absorbed into the surrounding air. So your temperature profile is going to look something like this. Whatever is happening inside, at the boundary, there's going to be a slope dictating that Fourier's constitutive relation is leaving heat from your material, and it's being absorbed and taken out by the convective fan blowing air across your system. So the heat leaving the material can be written as Fourier's constitutive relation, just like that. So this is the thermal conductivity of your solid material times the temperature slope, the derivative, evaluated at x equal to L. At that point, there's going to be a slope. This is the amount of heat leaving your material. Now, this must be equal to the amount of heat being taken out by the surrounding cool air. And some of you may have learned about this, but if you haven't, that's perfectly okay. There is a relationship called Newton's law of cooling. It looks something like this. This is called Newton's law of cooling. It says that the heat leaving the material and entering the surrounding air is going to be equal to the temperature difference from that point. So this point right here is the temperature at x equal to L. Okay? We don't know what the temperature is. We're trying to find what that is. So it's whatever temperature is at x equal to L, that point at the interface of the material contacting the surrounding fluid, minus the temperature of the air very, very, very far away. That's this temperature out here in the air very far away. So it's the difference in the hot surface of the material of your GPU and the coolant temperature very, very far away. That difference in delta T is multiplied against H, which is called the heat transfer coefficient. And the heat transfer coefficient tells you how much heat is being pulled out or convected out of the material. And there are tables and tables written in various textbooks about different types of heat transfer correlations or coefficients, depending on the air, the fluid, the substrate, various different systems combined. Once again, Newton's law of cooling is not really a law. It's just an empirically guessed relation. So if you compare the Robin boundary condition with this boundary condition we just wrote down, you can really see the comparisons. I'm going to rewrite this equation so that it looks more like what we have here. Just like that. So we have the function value right there. The function value has aspects of the Dirichlet boundary condition, plus we have the derivative. Added together, just like we have with Robin down here. So it's got aspect of Dirichlet, aspect of Neumann, and that is equal to a right-hand side, which in this case is equal to a constant. So here's an example of a Robin or mixed boundary condition that, as you can tell, seems very relevant in science and engineering. This is a real problem. I have friends who graduated with a chemical engineering PhD degree who works at electronics companies to do these types of considerations and at least think about basic scaling relations to just get back in the envelope calculations on, is the temperature cool enough? Is the fan speed large enough? These are the kinds of calculations that you can do quickly to get a sense as a scientist and engineer, are you setting up the system correctly? All right, so here are the different types of boundary conditions that you might encounter in science and engineering. Starting next time, we're going to leave the 1D heat equation because, after all, we don't live in a 1D world. We live in a 3D world. But let's first do 2-dimension. Let's talk about 2-dimensional heat transfer and see how we need to change the way we solve to make progress on a 2-dimensional case. All right, have a nice day. I'll see you next time.